You just go till you lose.
Yeah, you just go till you lose.
Yeah, I never won golf.
Well, let's
Do you
That's
get
a
to
good
keep
deal.
all your money that you gained? Yeah. this guy
Okay,
has over $1 million.
so along those lines, okay, get rid of that thing. So along those lines, calculus, we're playing a little calculus Jeopardy. Okay, so just, it's kind of not a lot of people here. We'll have a little fun, play a little calculus Jeopardy. So we all know the rules of Jeopardy, right? You have to answer in the form of a question. So the answer is, in this first one, the derivative is 3x squared.
What is x cubed plus c?
So the question is, what is f of x equals x cubed? But we do have to be a little bit careful. Did I not have the, okay, we haven't got to that part yet. Okay. So what is x cubed? Because derivative of x cubed is 3x squared, right? And we'll talk about the constant of differentiation soon, right? We're getting there. So what about this one? If the derivative is negative sine x, what's going to be the question? What is f of x equals cosine x, right? Would be one of the many examples. But we also could have done, could I not have also said like x cubed plus 11?
Yeah.
Or x cubed plus pi, or x cubed plus any constant? Same thing here, because when I differentiate, the constant's going to go away, right?
Not why we would just say x cubed plus c.
Which is why we will say that, right? Exactly. Okay, so then if we want to solve, when we want to kind of make this a little more mathematical, we don't talk about it as calculus Jeopardy. We talk about it as a differential equation, right? So a differential equation would be an equation involving a derivative, right? That's it. Remember, to differentiate means to take the derivative, right? So a differential equation is just an equation with at least one derivative in it, some level. Now, it could be, eventually, when you continue on with your study of calculus, here's kind of what the roadmap looks like. So this is probably the same for almost everybody. Like, we went through a whole series. We went through a calculus series, which is just regular, kind of calculus. And like this would be, for me, it was Calc 1, and then Calc 2 would be integral calculus, and Calc 3 would be the third one. And sometimes people skip into higher level calculus classes, but not often. Usually people just would typically start with differential calculus and do it again in college. I would encourage you to do that. You don't have to. You can try to test out of it, but I think it's generally a pretty good idea to just do really well in your first calculus class and just feel really confident. It's sometimes, depending where you're studying, it'll be a little different. It might be a little more theoretical. It'll be a little different approach. There might be a little more proof in it, right, at the college level. But anyway, you get through that first calculus series where you're going to do differential calculus and integral calculus, and then you'll do multidimensional calculus where you've got multivariable calculus, and typically you'll end up with some discrete stuff in there, sequences and sums involving some calculus. But then after that, you jump into a whole series. If you're going to stick with physics or electrical engineering or mechanical engineering or something like that, or math, you're going to go through a whole series where you're just solving differential equations, right? Where you do it in ways that aren't just where you're specifically starting with differential equations and trying to find all the solutions of those. And it's very interesting. It's a lot different now than it used to be. Now we can do a lot of this stuff symbolically with computer algebra systems where you can let, like a TI-89 will do a lot of this for you. Back in the day, way back in the day, we didn't have that stuff. And so we had to just crank through lots of differential equations. You have to know all the different forms. Is it an ordinary differential equation? Is it a partial differential equation? Is it homogeneous or non-homogeneous? And there's a whole series of things you study that have to do with the different approaches you would take to solving these differential equations. But differential equations, and when we get a little further on in the class, I do want to spend a little time kind of talking about the physics of them and why they work. If you want to do something like, if you want to model the behavior of, let's say take something simple like a vibrating wire, like on an instrument, right? Think about how you're going to do that, right? Modeling the string is sitting stationary is not very interesting, but when you pluck a string on an instrument, it sets up it vibrates in all kinds of distinct patterns. Right? If you want to represent the way that thing vibrates, that's a dynamic problem, right? So you want to know there's a lot of change going on in there. If we were to look at the string in profile, like here's one endpoint and there's one endpoint, like this is what we would call the fundamental mode of vibration, where the whole string just vibrates back and forth. okay? This would be what we call the first harmonic. If it does, have you guys talked about this stuff in physics a little bit?
Yes.
Okay, so the interesting part of this, though, is when you're solving these kinds of equations, there's going to be a lot of motion of the particles vertically, right? Assuming that the string is set up horizontally, there's going to be a lot of transverse motion of the particles that make up the string. Except, where is it not vibrating? At the nodes, okay? And different places, we're going to get nodes that sit on we're going to get nodes that sit on antinodes. And so even though it might be a node for one harmonic, it may not be a node for a different harmonic, right? But there's two places on that string that are always going to be stationary. The endpoints, right? And so when we set up a differential equation, we would do things like we would say, what are the initial conditions, or we might call them the particular conditions. And one of the things we'd say is we want to figure out how is the position changing. That sounds like a derivative, right? Things are changing with time. But we want to know how is that going to happen when these points at the ends of the string are fixed with some boundary values, like they don't vibrate. And that changes a lot of the answers that we get when we do this calculus. Now, there's a lot of stuff I just threw at you theoretically, but you'll start to be able to maybe in the back of your mind just hold some of those thoughts as we go through. I don't know if we'll get to that far today, but when we start looking at solving some differential equations, you'll kind of start to see how maybe you can see a connection between solving differential equations like this and the really simple ones that we're doing here. We're only going to solve ordinary separable differential equations in this class. But those give you a little bit of an idea what it eventually looks like when you solve other bigger, badder differential equations. Okay? So this differential equation, it involves a derivative. Well, you already get an idea what the solution is going to look like, right? We just have to play calculus Jeopardy and ask ourselves, what would I differentiate to get 2? Well, I'd get 2x, but there also could be a constant in there, right? And so we have to account for the fact that we may have attached some constant to that function originally, and it would have gone away when I differentiated. So we've got this uncertainty in what the original function is going to be that we differentiate to get this, and so we have to add a c. We'll talk more about that in the future, right? But this is what we'd call, the general solution to this differential equation that we started with. This is the differential equation, and that's the solution, right? To solve a differential equation, here's one simple way to think about it. It gives you an idea of what you're doing. You're just undoing the derivative, right? That's it. The solution to a differential equation is the function without the derivative. Okay? This is what you differentiated to get this. Yes, sir?
So is that the same as before?
It's different language, and they mean essentially the same thing. Yeah. Mm-hmm. And so this one, we already did this one. That's just going to be x cubed, right? Plus c would be our general solution to that differential equation. Okay. So now, how do we represent this, right? How do we represent the process of solving this equation to get that answer? Okay, so that's kind of next step probably. So we do this by taking what's called an indefinite integral. So in calculus, we throw lots of words around. Antidifferentiation is essentially equivalent to what we call in calculus integration. Okay, and why is it called integration? To integrate means to sum things up or to bring things together. And right now you can't, at this point, there's no way to see why those two concepts would go together. But shortly, we will get to that within a week and a half or so. We'll start to talk about how is this anti-differentiation process really a process of summing things up. It's not obvious at all that it is that at first. Because right now it just looks like we're undoing derivatives. So an antiderivative we would call an integral, and specifically we're going to call it an indefinite integral because of the existence of that c, right? We don't really know without some additional information what would the value of c have been, because it goes away when we differentiate, okay? Okay, so here's sort of the anatomy of an antiderivative or an indefinite integral. Here's how we write this, okay? So if I want to undo some function, like for example, if I'm going back, oh, I got that extra page. If I go back to this page right here, I've got this function that I'm starting with, and I'm trying to figure out what did I differentiate to get that, right? Well, that shows up underneath, inside this sign that we call an integral sign, right? It's all it is a lowercase Greek sigma. So it's like an uppercase Greek sigma means sum. Remember that from pre-calc last year? Capital sigma just looks like that. Okay, that's the symbol we use when we're taking a discrete sum. We're adding up pieces of something, right, in increments. Right? We could sum something like, what would this be? If I sum I from 1 to 5, what am I going to get? Just 1 plus 2 plus 3 plus 4 plus 5, right? So we're adding up a discrete sum of pieces that are discrete. They're not continuous. Okay, why is this related to that? Once again, it's a mystery for now, but this is just a lowercase sigma. Okay, you'll see why though soon. So the part that's inside is called the integrand. Okay, that's the part that we're trying to undo. And then we always have to put at the end of this, we're putting d whatever the variable of integration is, so what the independent variable is. So for us, usually it's going to be an x. And then the answer we're going to get back is going to be in the form of a general solution, and it's going to have the antiderivative, so the answer to Calculus Jeopardy, plus some constant of integration. Okay? Okay, and one other thing I want to just point out really quickly, and we'll come back to this, is that there's a strong inverse nature here. Antidifferentiation and differentiation, or differentiation and integration, it's easier to say integration, they undo each other in much the same way that if I had something like, let's say we have the function f of x equals x cubed, and let's say g of x equals the cube root of x. Well, what's f of g of x? X. What's g of f of x? They undo each other, right? These are inverse functions. Now, we can't say that derivatives and antiderivatives are inverse functions because they're not, but they have an inverse nature. They undo each other. So if I take the integral, the antiderivative of a derivative, what happens is they cancel, right? The antiderivative and the derivative cancel, and I end up with just the original function, now plus some constant of integration, right? But it undoes, the derivative undoes the integral and vice versa. If I take the derivative of an integral, then what do you know? I get back what I was taking the integral of, the integral. Okay, once again, they undo each other. So what that allows us to do then is it's going to allow us to make a connection between a differential equation and a solution, but in a way that's going to use this new integration approach. Okay, so like if we know, for example, you'll understand what I mean in a second. So if I take, this is a standard form of a derivative that we know, right? We know that the derivative of sine x equals cosine x. Okay, so if I want to undo that derivative, here are the steps that we go through. Oops, I don't have it. I do a little work here, I guess. All right. So first thing I'm going to do is we're always going to put the derivative into differential form, right? So do you remember, boy, it's when we did, it would have been back when we were talking about implicit differentiation, right? We talked about putting things, briefly we talked about putting derivatives in differential form. So the differential form of a derivative, remember, is what you get when you multiply each side by whatever's on the bottom of the derivative. So I would do this by multiplying each side by dx, and those would cancel, and I end up with the derivative of sine x equals cosine x dx. So that's the differential form of that derivative. Do you guys remember talking about that? Vaguely, I mean, it's been a while ago. It wasn't a big deal at the time, necessarily, okay, but it is a bigger deal now. So what does this do then? This is telling us, what this is saying up here, they mean slightly different things. This is saying that the rate of change of sine x, if I move along the curve, the slope is going to be cosine x, right? This is telling me that if I break a function sine x up into pieces of sine x, they're going to be cosine x times these little increments of change in x. And as we go along with this a little bit further and we start talking about the summation process, we'll have something to look at conceptually that will explain kind of why we do this. But for now, we're just changing the notation. There's a one-to-one correspondence. If you looked in a table of derivatives, you would see that you can either write them in this ratio form, where you're taking like dy dx, or you could write them in this differential form, where you're just multiplying each side by dx, so there's nothing on the bottom of the derivative. But they essentially mean the same thing. Here's why we do this though. Now we want to undo the derivative part by integrating both sides. Okay, so if I go through the process that I'm going to take an integral of both sides of this, an antiderivative, that's the inverse of differentiating. And then look what happens. Those cancel. So by integrating a derivative, we're undoing the derivative. And what do we get on this side? Just sine x, right? Plus some constant. What do we get over here? Well, we get this. We get the integral of cosine x dx. So what does that help us with? Well, that tells us that we get a new formula. We get an antiderivative formula that came from our original derivative formula, right? Doesn't this make sense, though? Before we said the derivative of sine x equals cosine x, right? Now we're playing calculus Jeopardy, and we're just asking the question, the derivative of what is cosine x? Sine x, right? That's how we write an antiderivative. This is asking the question, essentially, the derivative of blank is that. In other words, what is the antiderivative of cosine x? Okay? That's all we're doing is playing calculus Jeopardy with that. So, what is the answer? Okay, you tell me what's going to be there's the standard form of the derivative that relates cosine to sine. What's going to be, you tell me, what do you think is going to be the integral form, the antiderivative standard form
The integral
that goes with that?
The integral of negative sine x dx equals cosine x.
Okay, so we know it's going to be in that form, right? Got to fill in those blanks. Okay, we're just playing calculus Jeopardy. So the derivative of what is negative sine x?
Cosine x plus c.
And the answer is going to be cosine x, and we call it c1. Okay? But if I'm anti-differentiating the function negative sine x, that's the same thing as multiplying -1 times the antiderivative of sine x. So we don't really want to write it that way because that's not very convenient to have the negative sign attached to the sign. What we'd rather do is think of that as being minus the integral of sine x dx equals cosine x plus c1. And for my standard form, I just want it to look like, I want to fill in this blank. I want to be able to say the antiderivative of sine x dx equals what? When I go to my table of standard forms, I want to know what's the antiderivative of sine x, not the antiderivative of negative sine x, or opposite of the derivative of sine x. So what would I do algebraically to get rid of that negative sign? Multiply both sides by -1, exactly, right? So then that's going to give me, if I multiply each side by -1, I'm going to get the integral of sine x dx equals, if I distribute it through over here, I'm just going to get a negative cosine x plus negative c1. But why would I have minus c1 when that's just a different constant? Right? What if c is 5? Then this constant's -5. It's still a constant. So instead, we'll just call it negative cosine x plus a different constant. Call it c. Okay, so that's our answer. The antiderivative of sine x dx is negative cosine x plus c. Okay? We could have gone through, I skipped some steps, we could have gone through that whole process. You know, we could have done, if we wanted to, we could have done this. We could have broken this up into differential form. I could have integrated both sides to undo the derivative, right? And I would have ended up with that, right? You get the idea, okay? And then we just are going to solve for sine x, okay? So this also points out another important relationship, important technique we can use. What did we always do? If I took a derivative of something like negative x squared, I could always just think about the negative as being a constant that's out front of something, right? Or if I had a negative 2x squared, we just put the negative 2 out front and differentiated and then multiplied by the constant at the end. We're always able to pull the constant out front, as we can say in calculus. We can do the same thing with integrals. If I have a negative number inside, a negative constant inside the integral sign, I can always pull it out front and just deal with it later, right? To simplify what we're actually doing inside, which is the hard part, the integral part, okay? So we get then from this, we're going to get a whole list of different standard forms of integrals. And I'm not going to pull it up, but I'll give you a printout of that. For every differentiation standard form that we have, every standard form of a derivative, there's going to be a correspondence to the antiderivative. It's 1-to-1. Every time we learn a derivative, we also get with that an antiderivative, right? So for example, you tell me what if we did, and this is kind of a weird standard form, but if I take the derivative with respect to x of secant x equals, what is it?
Secant x tangent x.
What's the corresponding antiderivative that goes with that?
The integral of secant x tangent x dx equals secant x plus 1.
Right, so I'm just working backwards, right? So the antiderivative of whatever we got for our answer is just going to equal secant x plus c, right? And how about cotangent? So what if I did the derivative with respect to x of cotangent x equals negative cosecant squared x dx? This isn't one you use very often, but think about that for a second. Somebody raise your hand. Tell me what's going to be, can anybody volunteer, what's going to be the corresponding antiderivative that goes with that? What do you think? The antiderivative of what? Dx equals what? What do you think?
So the negative, the negative outside.
Okay, so we could put the negative outside. Cosecant squared x dx equals cotangent x plus, I'm going to call it C1, but then we really would rather not have that negative out front, right? So what are we going to do? Multiply it through, right? And we end up with antiderivative of cosecant squared x dx equals negative cotangent x minus C1, we'll just call it plus C, some other constant, right? And so that would be the standard form that goes with, for the antiderivative that came from our original derivative, right? Make sense? Okay? So you get, everything you know with derivatives, you get a corresponding, you get a new formula you already know for an antiderivative. Okay, what about this one? Let's just do one more of these. Everybody agree that's where we're gonna start if I just flip these things around? The antiderivative of this has to equal that plus some constant, right? That's not a very convenient way to write that, though, is it? Because think where we'd be using this. We'd be using this in a situation where we're trying to take, let's say we're trying to take an integral of say we're trying to take an integral of like x to the fourth dx, right? So that's not the form we want this in. We want this in the form something like the integral of x to the n dx equals an answer, right? We don't want to have to think about having this goofy constant out there that, who knows, when's that going to fit perfectly? Well, we want to be able to do, and if I had some constant there, like say we had a 4, well, that's just some constant that I could always pull out in front and just use my standard form, right? So how are we going to change? This is the correct transition from derivative to antiderivative, but how do I change that in a way that's more useful? What do you think?
Divide everything by k.
We could divide everything by k for one thing, right? That would be helpful. But then what about this part up here? Look at that. That's kind of goofy. I have x to the k minus 1. We'd rather just know what's the integral of x to the n, right? Because I want to think about that exponent in terms of what it is, not what minus 1 would equal that, right? I don't want to think of the 4 as being a 5 minus 1. I want to think about it as being a 4, right? So what else could I do? You're right, we definitely want to get rid of that k. Pull it out front and divide both sides by that. But what else could we do? Any ideas? What do you think?
Wouldn't it just be the constant of the derivative?
No, not necessarily.
Oh, no.
But there's going to be, I'm free to make a substitution if I want to. Like I could say, let this equal that, and I'll just use the new form. I can always make variable substitutions when I want to, or even like a parameter substitution. What would we want that to be? Not a k minus 1. We want it to look like an n, don't we? Right? So what if we just said, okay, well, we're going to make a little change here. We want that to be an n, because that matches the form that we want. So we can let n equal k minus 1, right? If I do that, what is k equal to in terms of n?
Plus 1.
Yeah, k would just always be n plus 1, wouldn't it? Right? So I could make that substitution. If I want to replace all the k minus 1s with an n, that's equivalent to saying k equals n plus 1. Okay, so then what's that going to end up equaling if I do that? So I'm going to get the antiderivative of x to the n, which is the same thing as n plus 1 minus 1. I just get my n where I want it. But what do I get out front now? Well,
Plus 1.
I get an n plus 1 out front. Okay, that looks a little bit inconvenient, but that's just some constant, isn't it? Right? Times dx equals x to the n plus 1 plus some constant. Well, now let's do Kirk's-Trick. Now let's factor out that n plus 1. We'll pull it out in front and divide both sides by n plus 1. Okay? So if I do that, if I divide both sides of this by n plus 1, those are just constant. N is not a variable. It's just some number, right? It could have been a 4 in this case, right? Or it could have been a 10 or whatever. It could be a negative exponent also. If I divide each side through by n plus 1, now look what we get. This looks better on this side. I get the integral of x to the n dx, which is what I wanted, right, is equal to x to the n plus 1 over n plus 1. If I split this into separate fractions, plus c1 over n plus 1. What should I probably call that?
C.
Right? It's just some other constant. N's a constant, c1 is a constant, so it's just some constant, right? So there's the formula we end up in. This is a super useful formula. This is what we call the power rule for integration. And we get tons of mileage out of that simple formula, but this is the way we want it. We want to be able to input something simple that's easily applied to a function that we're trying to integrate and get back something in terms of a formula that might be a little more complex, but we're just plugging in numbers for n anyway, right? So let's take this example then. What if we tried to do something, there's our formula. What if we wanted to do something like this? What if we want to do the integral of x to the 4th dx? Well, what's my n? 4. So the answer is going to be x to the 5th over Doesn't that make sense? Right? Because when we differentiate, we want to have something on the bottom to cancel with that constant when I bring it out front, right? Plus c. Okay, so what happens then if I want to integrate something that's got multiple terms in it, each of which has an exponent? What do you think you do? It's going to be, we're going to apply that rule, but the important thing, oh, I shall have it. The important thing to see about this is that just like I did with derivatives, when I differentiate stuff and I had a whole bunch of terms, didn't we just differentiate term by term? Well, doesn't it make sense that this is the inverse process of that? So I ought to be able to do the inverse of that process term by term as well. Because if we differentiated, we got separate individual answers for each term that we differentiated and just combine those into our one answer, right? What's the difference if we reverse that process? For each of those individual terms that we got when we differentiated, we'll just reverse the process and undifferentiate them individually as terms. So you don't have to write this all down, but when you're doing problems like this, what you want to think about at least is breaking each of these into separate integrals. I'd pull the 3 out front. That's all I'm doing, right? Okay? I wouldn't write all that out because it takes too much time, but when you do the process, that's what you're thinking. So what is the antiderivative of x to the 7th? Right? X to the 7 plus 1 over 7 plus 1. Okay, minus 3 times the antiderivative of x cubed would be x to the 3 plus 1 over 3 plus 1. And then what about this guy? What's the antiderivative of 1? Right? That's the same thing as x to the 0. So it ought to be x to the 0 plus 1 over 0 plus 1. So it's just x, right? Do you see that? Okay. And then what do I have to put at the end? C. Each one of those would have contributed its own little constant, but we'll just always consolidate all the constants together into one big C at the end. Okay? And that's it. Right? Okay, so we out here at 10, right?
Uh-huh.
Okay. Okay, so we can skip all that. All that. Okay, how could we do this one?
Negative x.
It could be, yeah. How would I rewrite square root of x? 1/2. Okay, and that would be negative 1/2, right? So we would just think about this then as being, even if we don't write it down, we've got the integral of x to the 1/2 plus x to the minus 1/2 over 2. And we'll just anti-differentiate or integrate term by term. Okay, so Emily, what am I going to get from this one? What's the antiderivative of x to the 1/2?
X to the 1 and 1/2. So 3
Yeah, so 3/2, good.
3
3/2,
halves.
so 1/2 plus 1, divided by 3/2, but we don't divide by a fraction, instead we multiply by reciprocal. So we would just do that. Right? How about this one? Liz, what's going to be the derivative of x to the minus 1? I'm going to pull that 1/2 out front. There's that one. How about this guy? Then I'm going to get x to the 1/2, good. Over 1/2, which would be times 2. Right? And then I can't forget plus c. Okay? All right, so now, what about something like this? Last problem I want to get through this. Okay, so this time we're given a differential equation, dy dx or y prime equals 2x minus 1. Now if I solve that thing, let's solve it first of all, see what we get. So how do I undo that derivative? So y equals what? How would I write this using calculus notation?
Integral of.
Okay, integral,
Two
antiderivative.
integral, my bad.
Well, no, I can't do that. I gotta do, because the 2 is only attached to the x. So everything that was there, right, the answer to my derivative becomes the integrand, right? What's inside the integral. And then at the other end, I've got to enclose that with the dx. Okay, that's my variable of integration. So what's the answer to that then? We can just integrate that term by term. What am I going to get for the first part of that? Lily, why? What's the derivative of 2x?
Just the normal derivative?
I mean, sorry, the antiderivative, sorry.
Okay.
Yeah, so I said that wrong, sorry.
Just x squared.
There you go, x squared, right? And instead of, see, I like what you did. Instead of thinking about that in terms of some kind of power rule, sometimes it's easier just to play calculus Jeopardy, seriously. Sometimes it's easier just to reverse the process of differentiating. Okay? And you'll just kind of know when to do that and when not, when you do this in a little bit. What's the antiderivative of 1? X, okay? And then I got to include my plus c out there, right? So what do you think it looks like when you graph x squared minus x? Well, that's a parabola, right? It's a parabola with, this could be a parabola with x-intercepts at 0 and 1, right? Well, that's that one right here. Okay, that's that. It's that curve right there, isn't it? Right? But that's only one of the possible curves we could get. That happens to be the one associated with c equals 0, right? But c could be anything, right? What's the relationship between the different curves we get when c takes different values? Well, if c is 1, what does it do if I add 1 to a function?
Raise it 1.
Offsets it vertically by 1. If I add 10, it offsets it vertically by 10. So what you end up getting when you graph, or when you find an antiderivative without any specific information, we find a general solution. Remember, that's what we call this, a general solution. To the differential equation, right there. It represents a family of curves, what we call this, right? Family of curves is an infinite locus of curves, infinite set of curves. Each curve, we call it trajectory. We talk about this in differential equations. Each curve, each trajectory corresponds to a specific value of c. There's an infinite number of them, and they're all going to be stacked up vertically in this case, right? Okay, but what if we're going to be more specific about this? What if we know that this actually corresponds to a real situation or some interesting situation, and we know that in our situation, whatever x and y mean, when x is 1, y has to be 1. You see that none of these trajectories in this family of curves, they can never intersect, right? They're all, if they're functions, because they can't line up vertically. So there's only one of these trajectories is ever going to go through that point. How do we know which one?
Substitute in the equation.
Yeah, right. We've got, once we get this thing solved, we end up with y equals x squared minus x plus c. Well, we know that if it goes through the point 1, 1, then y is 1 when x is 1, and we just get 1 equals 1 squared minus 1 plus c. Those cancel, and so I get c equals 1, right? So the particular solution, is going to be y equals x squared minus x plus 1. That's going to be the solution that corresponds to the one trajectory that we want. Okay? So, general solution, family of curves. Particular solution is the one trajectory of that family that satisfies some condition that you've placed on it. Now, different books are going to say different things about this. I really much prefer to call that a particular condition, right? A lot of times books are going to call that an initial condition, which is fine, but what does initial usually mean in physics? At the beginning when time equals what?
0.
0, right? And so a lot of times when you get into the physics aspects of this, you want to distinguish between, is it truly an initial condition? Is it a condition that's happening when at t equals 0? Or is it some downrange condition at a later time, which we call a particular condition? So in engineering and physics applications, sometimes it's important to make that distinction. Okay, one really cool thing you can do with this, oh man, I got 1 minute. I was going to show you guys how to, I was going to derive all the kinematics equations from this, 'cause it's really cool. We'll do that tomorrow. Yeah.
So we'll see always equal y intercept.
Will C always, no, it will not. It won't, because sometimes you could have, it won't. Because sometimes you'll end up with constants that show up like as multipliers. Like what if it's I know what you're saying, like if it's an algebraic function like this, yes it will, but what if you had like we'll look at some cases before you guys go for the summer, we'll look at some cases where we're gonna go back and look at logarithms and exponential functions using antiderivatives, and then sometimes that constant gets, by the properties of logs, gets wrapped back around as a multiplier. See what I'm saying? So it doesn't always. There's some cases where it would. Many times it is. It's a good question.
And